So in this video, I'm going to be answering a question that I'm not really sure that anybody's ever thought to themselves before, but my question is, how fast can you make an LED blink with an Arduino? Or more specifically, how fast can you toggle a pin on an Arduino? Now, first off, I should lay some rules out for this challenge. One, when I say Arduino, I mean an ATmega 328P based Arduino, so one of the older types. For example, an Arduino Uno. And the chip on this Arduino needs to be running at 16 megahertz. So all of the tricks that we're going to use are going to be purely software. We're not going to be changing the hardware or doing anything crazy like overclocking the microprocessor to get the LED to blink faster. We're just going to be doing software changes. I will also say that we don't need to use the built-in LED on the Arduino. We can use any of the digital I/O pins. Does not matter whether it's pin 13 or any other pin, really. So anyway, let's start with the basic blink sketch. I think everyone's pretty familiar with this. It's pretty simple. You just have the first line here in the void setup is pin mode. You set the pin mode of the built-in LED to be an output, which that's pin 13 in this case. And then in the void loop, you run the output high, you wait for a second, set the output low, wait for a second, and then that just repeats over and over and over. And that gets you something that looks like this. You have the pin 13 LED, which is labeled L on this board, blinking at a rate of 0.5 hertz with a 50% duty cycle. You can see the frequency measurements as well as what the waveform looks like on the scope in the background. Now, this is pretty much the first sketch that everyone runs on the Arduino, and it's a good test just to see if your board is still alive. I think the second sketch everyone runs on an Arduino is this same one, but with the delays slightly tweaked. So if we take a 0 out of the two 1000 millisecond delays and we make them 100 millisecond delays, we get something like this. You see our LED is blinking quite a bit quicker, and we're blinking at 5 hertz now instead of 0.5. Now we can take this concept a little bit further and we can actually get rid of all of the zeros, so our delay is only 1 millisecond. And this is going to be a pretty significant frequency increase. And we can see we're at 500 hertz now, still at 50% duty cycle. And you'll notice that the LED on the Arduino doesn't really even look like it's blinking anymore, it just looks like it's on solid. If you were to pick up the Arduino right now and start waving it around, you would see that it is blinking. I'm not going to do that in front of the camera because the camera might not pick it up, and also it's kind of tied in by my oscilloscope right now. So anyway, the next logical progression here is to just completely get rid of the delays in their entirety. So if we upload that, see there's another big frequency increase. And we're at about 147 kilohertz now, and still around that 50% duty cycle number. One odd thing I've noticed is that at this point, the LED quits illuminating on the board. I don't know if there's some weird low-pass filter effect going on here, or why that actually stops lighting, but I lose the LED. I don't know what the reason for that is. So the next question is, what do we do now? We're already down to 2 lines of code. We're still at 150 kilohertz, a little less than 150 kilohertz, which is really quite slow compared to the clock frequency, the 16 megahertz clock of the microcontroller. And I think we should be able to go way faster than this. So of course, the next thing you do is you ask ChatGPT. And we tell it to write Arduino code to blink an LED as fast as possible. We'll see what we get. Well, that's kind of disappointing. We get the exact same code that we already have. And it just tells you as quickly as possible. It says, note that the speed of the blinking LED may be limited due to the Arduino board's processing speed, so it may not be possible to blink the LED at the absolute fastest speed possible. I don't really know what that's supposed to mean. Interestingly, I have run this prompt a few times through ChatGPT, and it actually gives you different answers. Or I've gotten two different answers so far. I've gotten this answer and I've gotten this answer, but with a 1 microsecond delay between the digital writes. But anyway, ChatGPT doesn't think it's possible to go any faster than what we already have. But I think it is. And I think we're going to have to do some things that are a little bit more complicated to get there, but I think we can indeed get there. So one thing that you need to understand is that these digital write commands are written to be sort of universal and easy to use with different Arduino boards. That's great and all. Problem is, they're super, super slow. And we're going to make one change. We're basically just going to go through and replace all 3 active lines of code in here with 3 slightly different active lines of code that'll do the exact same thing, but they're going to execute way, way faster. So if you've done Arduinos for any real length of time, you've probably seen a pinout image like this before. You may have used this to find like what pins your I2C data lines are, or SPI, or what have you. And you've probably seen these labels that are in orange here, these ones that are like PB and PD, and so on and so forth. And you've probably just kind of ignored those because they don't really seem super useful. Maybe you've wondered what they're for. And we're going to talk about that right now. So we're going to take a quick look at the ATmega 328P data sheet. And what I'm going to show you is the pinouts of the actual microcontroller here. And you'll notice here that D13 says PB5 on this other label. And if you look at this sheet, you'll see that PB5 is right here. And you'll also notice that there is no such thing as D13. And that is because D13 is sort of an arbitrary label that the designers of the Arduino stuck onto pin PB5 of the microcontroller. Now, what does PB5 mean? Why is it called PB5? Why those specific letters and numbers? And you'll notice if you look at the rest of this, there's PD, PB, and PC. Now, P stands for port. So here we have port B, port C, and port D. Not really sure where port A went. Don't ask me that. I didn't design the thing. But we have these 3 different ports, and you'll notice that most of the ports are 8 bits wide. So there's 8 pins on every one of these ports. And these ports are controlled by things called registers. And registers are actually what controls every piece of the microcontroller, whether it's the I2C peripheral or serial or SPI or the GPIO pins, ADC, everything. Everything is ran by a register somehow. And a register is effectively just a space in the CPU's memory. And we can access that memory pretty much just like it's a variable, especially with the Arduino IDE. You can literally just call these registers as if they were variables that are already declared. They're quite easy to use, really. They're quite easy to access, at least. A little bit confusing to use if you've never done it before. But what we do need to know is that D13 is on port B, pin 5. What do we do with that information? Well, in order to control a pin, we need to mess with 2 of these so-called CPU registers. Now, there are other videos that are probably going to be better at explaining what CPU registers are, but we're just answering a simple question here. And I'm going to tell you what you need to do in order to control a GPIO pin. We need first to set the data direction register, which is what DDR is short for. And we're working on port B, so we need to specify data direction register B. And then what I'm going to do is put OR equals, and this is just going to do a logical OR statement between what we're about to put in here. And I'm going to specify what we're going to put in here in binary. So in order to specify binary, in C, you start your number with 0B, and then, like I said, we have 8 bits to work with, so 1 byte of memory. So we're going to just put in 8 zeros for now. 1, 2, 3, 4, 5, 6, 7, 8. So 8 zeros, and we of course end that with a semicolon because it's C. Now, what you need to know is that PB0 would be this rightmost 0, and PB7 would be this leftmost 0. And we want to mess with PB5. So that's going to be the third 0 from the left here. And with this particular register, if you have something set to 0, it's going to act as an input, and if you have something set to 1, it's going to act as an output. Now, the magic of doing this little or equals thing is that when you set something to 1, you can set a single bit in this register to 1, and you don't affect any of the other bits. That's useful if you have multiple I/O pins that are being configured in different places. You can do it without this OR symbol in here, but it is safer and it's considered best practice to do it with that symbol. That way you don't affect any other pins. But what this is going to do is it's going to set PB5 as an output. If you upload this now, absolutely nothing's going to change because all we've done is we've changed this pin mode command to this. It's not going to make anything faster because we haven't done anything down here, which is where it's going to actually make a difference. So what I'm going to do is I'm going to copy this exact same line of code, and we're going to put it here. And I will comment out this one. The next thing that we need to worry about is the port register, and it's literally PORT-B, and we're going to do the exact same command. And what the port register does is it will actually control the output transistors of the microcontroller, GPIO pins. So setting this to 1 will make the pin go high, setting it to 0 will make the pin go low. Which by that logic means that we need to take this line of code again and put it down here. Now this is where things get a little bit weird. I'm going to continue using this quote-unquote proper notation of only modifying 1 bit at a time. And in order to do that, for turning a bit off, you actually do and then you do the inverse of what we did before. And that will just make it so that we're only controlling one single GPIO pin. We're going to come back to that here in just a second. But we'll upload that, and you'll see that our frequency has already increased substantially. And you'll see now we went from 150-ish kilohertz all the way up to pretty much exactly 2 megahertz. Though our duty cycle has dropped, oddly enough. Our duty cycle is down to about 25%. Now, the reason why our duty cycle dropped is pretty simple when you think about it, but it's not immediately obvious. So if we run through this loop, we first turn the LED on, and then we immediately turn it off, and then we go back to the start of the loop. Thing is, there is actually a command in there, an instruction, and it does take some amount of time to go from the end of this loop back up to the start. So that's why we're seeing the 25% duty cycle, is because we're spending some amount of time looping back to the start. Now, if you remember what I said about only modifying 1 bit at a time, well, there's no real rule saying that we can't modify the entire register all at once. It's not a good practice to do because now I've just taken over all 8 pins on this port. Well, oddly enough, port B I think only has 6 pins technically, but anyway, we're using every pin that's on this port and we're just writing to it all at once. And I actually need to set that to 0 down here in order to turn it back off. So the thing with this is that when you call this function, or when you do this operation, you are reading data from the register, doing math on the data, and then writing the data back to the register. If you just do this, you are just writing data to the register. You're completely foregoing the read step, and you're completely foregoing the comparison step. So this just loads data straight to the register. Can't really get much simpler than this. And with that uploaded, you can see that our frequency has gone up to 2.6 megahertz. So it's just ever so slightly faster. Our duty cycle has also gone down a little bit further, down to about 16, 17%, which is interesting. It's kind of indicating that the thing that takes the longest here is actually the instruction to go from the end of the loop back to the start. Now, we could continue down this path of trying to optimize this thing. We could go into writing it in actual assembly language and things like that, but I just don't think it's really going to get all that much faster. But I have another trick up my sleeve. And for that trick, we are going to use this piece of code. Now, really, the only reason why I know anything about any of these registers is because I had to program Arduinos using this type of language back when I was in college. My sophomore year, I took a class called Embedded Systems, or Intro to Embedded Systems, and we learned all about this. We were not allowed to use digitalwrite or anything in that class anywhere. So these register things are interesting, but not necessarily the most practical thing, but you can learn from them. But what this piece of code does is it sets up PWM using timer 1 on the chip. Now, the trick with this is it actually uses digital pin 9 instead of digital pin 13 like what we have been using, and this is going to be really slow to start with here. But you can see this is a 400 hertz square wave at about 50% duty cycle, the way this is set up right now. I'm going to do my best to give a little crash course on what this code is doing and what these registers are actually doing. I could make a more detailed video on how to set up these timer registers if there was interest in that, maybe if there's enough comments below, or there's probably other people that have made better tutorials on this. But anyway, starting from the top here, we're doing the same thing. This is DDRB, so data direction register, or equals, and then we're just setting, in this case, PB1 as an output. That's doing the exact same thing we were doing in this piece of code where we were setting PB5 as an output. Next thing is this ICR1. So first off, I need to explain what these timers actually do. The timers are actually, and they're called timer counters, and the reason why they're called timer counters is because really what they do is they count things. So they start off at 0, and they just, every time there's a clock pulse that goes into them, they count 1, 2, 3, 4, all the way up to whatever you set this value to in this case. So this is going to count from 0 up to 40,000, and then when it hits 40,000, it's going to reset back down to 0. These two are the timer control registers. That's what TCCR is, and there's a few of these on the ATmega 328P. We're using timer control register 1. There is also a timer 0 and a timer 2. Anyway, we're not going to go into too much detail about what these two are specifically doing. Part of this is a clock prescaler, and I have the clock prescaler set to 1, so it's just using the fastest clock that it possibly can. And this last one is this OCR1A value. This is sort of a trip point. So this is what controls the actual GPIO. So what is happening here is this timer starts counting at 0. It will go 0, 1, 2, 3, 4, all the way up to 20,000. When it hits 20,000, the GPIO pin will go high, and it'll continue counting. So it'll start going 21,001, 21,002, and then it'll count all the way up to 40,000 like that. And then when it hits 40,000, the GPIO pin goes low again, and it starts counting from 0. And by doing this, you can actually create different PWM waveforms. So if we do 10,000 instead of 20,000, we can upload that, and we'll get a 25% duty cycle instead of a 50% duty cycle. And this is, in fact, exactly how PWM normally works with an Arduino. When you call analog write, it's using something to this degree in order to set that up. The other thing you'll notice is this is entirely executed in hardware. Because you'll notice here, there's nothing in the void loop whatsoever. The software in the loop does absolutely nothing. This runs once, it gets set up in hardware, that's it. It just goes forever once you set it up. But what we can do here is we can actually set this top value to 1. So what this is going to do is it's just going to count between 0 and 1. And we can set this value to 0. If we upload that, we are going to get a very high frequency signal of 8 megahertz. There we go. And a duty cycle of pretty much exactly 50%. And this pretty much concludes the video. This is the fastest that I know how to get a Arduino output pin to toggle. It's by using the timer in particular PWM mode. I think this is fast PWM, but that's something for a different video topic. But if you guys know of any faster ways to toggle a pin on an Arduino Uno, go ahead and let me know down in the comments. Perhaps we can make this sort of a challenge video. Other people can replicate what I've done here, or you know, we can do something. You guys can maybe come up with something faster. I don't know. Anyway, this is the best that I could come up with. And you know, if you found this video interesting, or maybe you learned something from it, or at least inspired you to go look up other YouTube videos on things like CPU registers, go ahead and leave a like. And if you're interested in the content, maybe consider clicking the subscribe button. And I'll see you in the next one, guys. Bye.